you for visiting Pathshala.com. As you can see, this is the second part of lecture from the topic element, compounds and mixture. And we begin this part of our lecture with the topic formula of compounds. Now, in our first lecture, we discussed what compounds are. In this lecture, we discuss their formulas. Every compound is made up of or has a formula. The formula shows the symbol of the elements and the ratio of the atoms they are made up of. For example, let's discuss water. Water has a chemical formula of H2O. From therein, you can discern that there are two atoms of hydrogen and one atom of oxygen. These two are combined together to form this compound with this chemical formula. Apart from water, there are several other elements with chemical formula. For example, chemical formula of a common compound that we use every day in our household is sugar, and its formula is C12H22O11. Another such a compound that we use in our everyday lives is salt, and it has a chemical formula of NaCl. One atom of sodium is bonded with one atom of chlorine, and here you can see that there are 12 atoms of carbon bonded with 22 atoms of hydrogen and 11 atoms of oxygen. Now guys, these are the common and the most simplest representation of all the atoms that are present in one compound. Now this kind of a formula that represents the simplest ratio of all the atoms, of all the elements in a compound, is known as an empirical formula. Following my lecture, I will provide you a table that contains the empirical formula of many compounds that we work with in our daily experiments in the lab, or we can see in our daily lives. The empirical formula. In Word, you see the names of all the compounds and their empirical formulas, the elements that make up the compounds and their ratio. In carbon dioxide, you see the empirical formula is CO2. The elements that make up carbon dioxide are carbon and oxygen, and the ratio of these elements are 1:2. Which means for every one carbon atom, there are 2 oxygen atoms bonded together, forming the compound. In case of sodium chloride, the empirical formula is NaCl. The elements present are sodium and chlorine, and the ratio is 1:1. In case of sodium hydroxide, the formula is NaOH, and the elements that are present are sodium, oxygen and hydrogen, and each of them are at a ratio of 1:1 with each other. This formula, the empirical formula, is basically what we see on the labels of everything, every chemical that we have come across in laboratories or in home that we have used or will use. However, there is also another formula that arises from the amount of molecules in a compound or the molecules in an element. What are molecules? How do we find out what a molecular formula is? This is what we will discuss next. Many substances are made up of molecules. Molecules are atoms that are joined strongly together by chemical bonds. And what these different types of chemical bonds are, their details and their characteristics, is something that we will discuss in a later chapter. As for this chapter, let's delve deeper into molecules. Now, like I said, molecules are atoms that are bonded strongly with each other. Many elements have molecules. For example, hydrogen is made up of molecules. hydrogen molecule, two hydrogen atoms are bonded strongly with each other in a bond known as covalent bond. Now, this is the formula of a hydrogen molecule. This, if I build this up in a diagram, I can make it, this will look like something like this. Hydrogen atoms that are joined strongly together forming a molecule. However, in this case, where there are two hydrogen atoms that are present side by side, these are two separate hydrogen atoms. They are not attached strongly within each other. They are not bonded. So, they are two separate atoms of hydrogen. This is not a representation of a hydrogen molecule. How we chemically represent this form of hydrogen is 2H. Note that the 2 in this case is in front of H, meaning that this is a representation of two different atoms of hydrogen. And in this case, the 2 is underneath, meaning the two atoms of hydrogen are bonded together forming a molecule, also known as a diatomic molecule of hydrogen. Like hydrogen, many other elements also has molecules. Now, if you were to take a balloon and fill it up with hydrogen gas, that balloon will contain many molecules of hydrogen gas. Now let's move to another element, oxygen, for example. Oxygen also has a formula O2, meaning two atoms of hydrogen are bonded strongly with each other forming one molecule of oxygen. This is similar to that of hydrogen. Another such an example of an element containing molecules is sulfur. The formula of a sulfur molecule is S8, which means one molecule of sulfur contains a ring of 8 atoms. A ring of 8 atoms of sulfur joined together. This forms a molecule of sulfur. Now, molecules are not just found in forms of elements, in elemental form. Molecules can also be found in between compounds. For example, carbon dioxide, as we have discussed before, carbon dioxide, water, etc. They are made up of molecules. But not all compounds are made up of molecules. For example, metals are not made up of molecules. Metals and other metallic compounds, they do not have a molecular structure. For example, sodium chloride is one such chemical wherein sodium is the metal, chlorine or the chloride ion is the non-metal. The relation in this bond is that of where sodium has a positive charge and chlorine has a negative charge. So they are attracting each other. As a result, they are forming the chemical bond. But there are no molecular structure in this case. And this is the same wherever you can find a bond between a metal and a non-metal is where you might not find molecules. Now, usually, compounds has the same molecular structure, molecular formula, Compounds tend to have the same molecular formula as their empirical formula. Like I mentioned at the beginning of this lecture, that empirical formula is one where in a compound the elements are present in their simplest ratio. So an empirical formula of carbon dioxide is CO2, where carbon and oxygen are present in their simplest ratio. So if I were to talk about one molecule of carbon dioxide, its molecular formula will be the same as that of its empirical formula, because one molecule of carbon dioxide has only one carbon atom and 2 oxygen atoms. And it's the same with water. If we were to discuss about the molecular formula of water, the formula is H2O, which is also its empirical formula. But is it the same with every other compound that forms molecules? No, not so much. For example, let's delve into a little complicated, a complex structure. I'm sure each and every one of you have ridden cars, and you have heard of car fuels, butane for example. The formula of butane is C4H10. Here you can see that for in this formula there are 4 atoms of carbon and 10 atoms of hydrogen. But this is the molecular formula of butane. But if I were to take it to its simplest ratio, the simplest ratio of carbon is to hydrogen, wherein I am to find the empirical formula. Note my words carefully, guys. This is the molecular formula of butane. Butane is what? Butane is a fuel which we use in cars or other machineries. Now, if I am to find the empirical formula, I will see that its empirical formula is something that looks like this, C2H5. So, for every 2 atoms of carbon, there are 5 atoms of hydrogen. So, this is the molecular formula of butane, and this is the empirical formula of butane. So although a lot of molecules may have the same empirical and molecular formula, we may find that there are molecules that are higher up the chemistry ladder, higher, more complicated. When you delve into higher chemistry, you will find that there are compounds whose molecular formula are a bit more complicated than their empirical formulas. Now, this far, we have discussed about elements, compounds, mixtures, molecules, and the two different kind of formulas, the empirical formulas and molecular formulas. One thing that does come to my mind, I don't know if it questions yours, is that how do their skeleton look? Like, we are human beings, right? We know how our hands or feet or our whole body may look as a whole. The idea about chemistry is you just know them by theory. You don't really know or have an idea of how their structures may look like. So in the next part, we are going to look at the structural formula or the structural compound of different chemicals. So guys, like I mentioned, every molecule has an every chemical compound has an empirical formula and a molecular formula. And molecules are atoms of elements that are bonded strongly together. Now, molecules also have a structural formula. What is that? A structural formula of a molecule shows clearly how each and every atom in that molecule are bonded. A structural formula shows the atoms that are, situated apart, joined by single or double lines. The single or double lines represent the number of bonds that are bonding these atoms together. For example, let's say sulfur dioxide. Sulfur dioxide has a chemical formula of SO2. This is a molecule where there is 1 atom of sulfur joined together with 2 atoms of oxygen. Now, if I were to draw a structural formula, aka an anatomical representation of how exactly the sulfur atoms are joined with the oxygen atoms, it would look something like this. There is sulfur, and this sulfur is bonded, and this line represents the bond between sulfur and oxygen. And this sulfur in turn is bonded with 2 atoms of oxygen. And this whole representation wherein you can see how the structures are attached with one another is known as the structural formula. This bond that has the atoms of different elements attached to them is known as a covalent bond. Details of this bond, again, I have to repeat myself, the details of this bond will be discussed in our later chapter. Now, this is a representation of the structural formula of sulfur dioxide. Let's see another formula. Some time before, before the beginning of structural formula, I mentioned butane, wherein I said butane is a chemical compound which has a chemical formula which looks like this, C4H10. So what if I had to draw a structural formula of a butane molecule? How would that look like? So we start with 4 carbon atoms, each carbon atom bonded with each other by a single covalent bond. And then we have 10 hydrogen atoms. So we put in more bonds wherein the hydrogen atoms may sit. So we have 4 hydrogen on top and 4 hydrogen at the bottom. So we have C4H8. Now there are 2 more hydrogen atoms left, which we can position here and here. So this, guys, is the structural formula of a butane molecule. This is the molecular formula and this is the structural formula. Coming next will be a table which shows you the structural formula of some common compounds. If you want, you can note down those formulas and the structures in your lecture or your note copy, whichever you prefer. So guys, this table represents the name of the molecules, the molecular formula and the structural formula of a couple of well-known elements and compounds. For example, hydrogen. Hydrogen is an element whose molecular formula is H2 and the structural formula of a hydrogen molecule is 2 hydrogen atoms bonded by 1 covalent bond. In case of water, the molecular formula is H2O, as we all know by now, and the structural formula is 1 oxygen bonded with 2 atoms of hydrogen. In case of sulfur trioxide, we have 1 sulfur atom bonded with 3 oxygen atoms. Now one thing to be noted here, guys, is that each bond with each oxygen atom by the sulfur has 2 covalent bonds, unlike its predecessors. Its predecessors had 1 covalent bond each for each molecule, for each atom. In here, you can see sulfur is bonded with oxygen by 2 covalent bonds each. Now let's go to methane. Methane is what we know as our cooking gas, the gas that you use or your mom uses or anybody in your home uses to cook every day. Methane has a molecular formula of CH4 and it looks like this: carbon bonded with another carbon atom and the carbon atoms in turn bonded with 2 hydrogen atoms. Let's move on to ethanol. Ethanol is an alcohol. It is used in many different purposes: perfumes, nail polish removers, nail polishes, sprays that you use in your homes, anywhere you name it. If you look at the chemical label on it, you can find ethanol. Ethanol has a molecular formula which looks like this: C2H5OH, wherein there are 2 carbon atoms bonded together by a covalent bond and there are 5 hydrogen atoms, C2H5, and there's one hydroxyl. This is to be remembered. Guys, please don't confuse the OH here with the OH that you generally see with sodium on OH. With sodium hydroxide, you can see that in sodium hydroxide we naturally see that there is NaOH. This is hydroxide. This is in case of metal hydroxide, but this right here, this is the hydroxyl group. This is found in alcohols. Now, ethanol has a formula C2H5OH, C2H5OH. Now, since the space is a little bit depleted here, my drawings of the structural formula can look a bit misshapen, so I apologize beforehand. Let's move on to our last one, ethanoic acid. Ethanoic acid, also known as vinegar, has a chemical formula of C2H5COOH, and it has a structural formula. As you can see, carbon atoms are bonded within each other and also bonded with hydrogen atoms. And in here, the COOH group, which is also the organic acid group, or the carboxylic acid group, something we will discuss when we are talking or we are learning organic chemistry. But for now, you can see that each carbon atom is bonded within each other, and also this carbon atom is bonded with oxygen, which is in turn bonded with hydrogen. And in here, the carbon atom has a double covalent bond with another oxygen atom. So, this table represents a couple of known molecules, their molecular formulas and their structural formulas. And if you want, you can note them down in your note copy or wherever you want to, and I hope they're helpful. At this last part of our lecture, which is also the final part of part 2 and the final part of this chapter, element, compounds and mixture, we will discuss about chemical equations. What are chemical equations? Chemical equations are representations of chemical reactions happening. We say that when hydrogen is combined with oxygen, water is formed. We say that when magnesium is burned in oxygen, magnesium oxide is formed. When we say that when we burn coal or when we dissolve salt in water, salt dissolves and it is formed into its respective ions and reaction happens. But we do not know for sure what happens. An equation is representation of the reaction happening. Now, we can say, we can write these equations in forms of words and also in forms of chemical symbols. In O-level chemistry, you will find that you may have to do both. Sometimes in your exam paper, sometimes while you are depicting a comprehensive reaction taking place. For example, when we will learn about extraction of iron happening in a blast furnace or the electrolysis of copper sulfate, we have to actually say what's happening in each chemical reaction at each stage in words as well as show them in chemical symbols. So chemical equations are depictions of reactions happening in form of word. For example, let's say burning of magnesium in oxygen. If we were to do that, we start with magnesium, and this is the word equation part. This is the part where I show you how to write a word equation. So, magnesium solid, magnesium plus oxygen forms the compound magnesium oxide. This is a word equation. Word equation. The short form of equation is EQ. If you wanted to write in a short form, you could write it like this: EQ, N on superscript. So this is in word form. What if we had to write the same thing in with chemical symbols? So we delete the word from here. We write chemical equation. And we change the respective elements to their symbols. So we start with magnesium, and then we have oxygen. Magnesium reacting with oxygen forms MgO. This is again an unbalanced equation, so let me balance it for you. In here we have one atom of magnesium, in here we have 2 atoms of oxygen. Here we have 1 atom of oxygen and 1 atom of magnesium. So if I were to put a 2 in here, this means that right now we are conducting an experiment with 2 atoms of magnesium and 2 separate atoms of magnesium and 2 atoms molecule of oxygen. So there's all still an imbalance, 2 here, 1 here. So if I put a 2 in front, we have a balanced amount of magnesium and oxygen on both sides of the equation. And this is how you write a chemical equation. One more thing that you always have to remember while writing a chemical equation are the state symbols. Now, what are the state symbols? Many times I'm sure that you have noticed that in a chemical reaction there are always a few words, a letter or 2 words that are written in brackets underneath each chemical symbol. You might have wondered what those mean and why do we need to say that, or why do we need to show that they are there? Well, those are the state symbols, which means that each of the elements that are represented by their symbols, the brackets show the state that they're in while they are taking part in the reaction. For example, in our previous experiment with magnesium and oxygen, the state symbol would have said S in here, and in case of oxygen, state symbol would have said G in here, forming MgO, which will also be S. So what does S, G and S mean? In state symbols, S means solid. L in short form means liquid. Sorry. G means gas. And there's also one special symbol that you will find basically everywhere in chemical reactions where acids or solutions are concerned. This is AQ, which means aqueous. And the word aqueous means that your reactant. One thing that I failed to mention at the beginning of this part of lecture is that in a reaction, the elements or the compounds that you are using to react, the elements or compounds that you are putting in before the reaction that are reacting to produce this. So the elements or compounds that you begin with, they are known as reactants. I will repeat myself. The elements or compounds that you begin your reaction with, that take part in the reaction, those are known as reactants. And when reactants react in a reaction, reactants reacting in a reaction forms what is known as products. So, the reactants will always have state symbols. The state symbols are as such solid, liquid, gas and aqueous. Aqueous means that your reactant, whatever it may be, it is dissolved in water. It has not become liquid by itself. It is bonded with water, as in it has become completely soluble in water. For example, if you react magnesium solid with hydrochloric acid, this acid is found in liquid form, but we still write aqueous. Why? Because what we do is we buy this acid in a powdered solid form, which we later dissolve in water, thus giving rise to the aqueous state symbol. The molecules of these acids are dissolved in water, giving rise to magnesium chloride, which is also aqueous, because this compound is found dissolved in water, not in solid or not in any other form. And hydrogen gas. So there you go, guys. Magnesium solid reacting with hydrochloric acid, forming magnesium chloride, which is a salt. The basis of acids, salts and bases is something we will discuss when we are learning or studying the chapter acids, bases and alkali. Now, metal reacting with acid forms the salt magnesium chloride, which is in aqueous state, and the gas, which is known as hydrogen, which is denoted by the state symbol G. So in here, magnesium and hydrochloric acid, they are the reactants, and magnesium chloride and hydrogen gas are the product. Now I will leave it to you guys to figure out the word equation, which is very easy. You write the name of magnesium and the name of hydrochloric acid reacting together, forming magnesium chloride and hydrogen gas. Basically, you write their names out without, remember, when we write word equations, we do not use state symbols. State symbols are something that are used only in chemical equations. So this is the chemical equation of the reaction happening. If we were to write it in word form, in their names, that will be the word equation. And this is how we represent a reaction happening in form of equations. Guys, this concludes the complete part 2 of the chapter Elements, Compounds and Mixture, and this is also the conclusion of this total chapter. I hope you have been able to follow through the part 1 and part 2 both in a complete manner, and I hope I have been able to help you understand different aspects and different chemical structures completely. And I hope you will be able to answer the questions in your textbook and your question papers efficiently now. And until the next lecture, have a nice day.